In this section, we are going to move from intrinsic silicon to silicon with impurity or dopants. I shall discuss how dopants affect the carrier density in the unit of per cubic centimeter. When dopants are added, they create something called the dopant state in the band gap. The carriers in the conduction and valence bands respond to the addition of dopants by adjusting the generation and recombination rates until thermal equilibrium is achieved. Besides changing the carrier density, the dopants also change the location of the Fermi level, and I shall explain how to locate the Fermi level in a doped semiconductor. To intrinsic silicon, some group 3 or group 5 elements can be added to replace some of the silicon atoms in the crystal. The common group 5 elements used to dope silicon is phosphorus and arsenic. Other group 5 atoms may not be suitable to be used as dopants, as their size may not fit into the place of a silicon atom. When an atom of a group 5 element, for example phosphorus, replaces a silicon atom in a crystal, it gives a core with one extra positive charge, but also an extra negative electron so that the atom remains neutral. But the extra electron cannot fit into the valence band because only 4 outermost electrons are required to form the covalent bonds with 4 neighboring silicon atoms. The extra outermost electron will be forced to go to the conduction band. Compared to a silicon atom, a group 5 dopant donates 1 extra electron to the conduction band. Therefore, they are referred as donor dopants. Silicon doped with group 5 elements are called N-type silicon. The letter N sort of represents the negatively charged electrons are responsible for current conduction. Similarly, an atom of a group 3 element, typically boron, can be used to replace a silicon atom in a crystal. When that happens, 1 electron is missing in the covalent bonds of the atom, resulting in a hole in the valence band. If the hole accepts an electron, the covalent bond is complete. The boron core becomes negatively charged, as it has 1 fewer positive charge in the nucleus compared with silicon. Therefore, the introduced boron atom can be considered as a negatively charged core, but with a positively charged hole such that it is overall charge neutral. Due to this property, boron is also referred as an acceptor dopant. When a silicon crystal is doped with a group 3 element, it is called a p-type silicon because its carriers mainly consist of positively charged holes.